Hi, everyone. Thanks so much for participating in our SNIA track at SODACON today. We've had some great sessions on computational storage management, and our final session will be on persistent memory with a video presentation by Jim Pfister, who directs persistent memory enablement at SNIA. I hope you'll enjoy
Hi,
it
everyone.
And ask questions.
My name is Jim Pfister, and I'm a SNIA independent contractor, and I work on the initiatives enabling for the SNIA Compute Memory and Storage Initiative. A lot of the things that you've heard today coming out of the track today are on computational storage. I actually want to wrap in another CMSI technology, which is persistent memory. We've been working on persistent memory longer than we've been working on computational storage. So first of all, I want to introduce the technology to you if you're not familiar with it. And then I also want to show you how we've been then proliferating a programming model for persistent memory based off of the programming specification that SNIA developed. And this gives you an indication of what we might be able to do long-term for things like computational storage, as we want to deliver that out to the market as well. So without further ado, let's jump into this. So first, what is persistent memory? Some of you might be aware of it, but let me give you a quick overview. If you look at the graphic on the right, what you can see is that you've got different levels of latency that you can use to access different memory tiers in your system. And some of those tiers are volatile and some of those are non-volatile. You can think of DRAM as being able to write to memory, but it is not something that persists. Power off or an application close would eliminate that data. Meanwhile, you can write to any number of storage devices, the hard drive, the solid state drive. Those do persist, and they have a lot of mechanisms and software history in place in order to be able to not only store that data, but protect it in case of crashes or failures or other things like that. But they take, from a computer standpoint, a really long time in terms of latency to access. So what we wanted to do as an industry several years ago was actually create a tier in the middle of that, what I would call persistent memory. So this would be a memory level device that would operate almost as fast as DRAM, but would then have the capability to drive persistence long term. Obviously, doing something like that, being able to do a direct access to a memory that would be persistent, requires some changes in the programming. And while we get that dramatic system performance increase, it does require a change in terms of the computing architecture. So from that perspective, we wanted to be able to understand that we could change applications, but do it in a way that was going to be able to be easy or relatively easy and benefit everybody involved. Now, if you're curious about the hardware, there's a variety of different memory types. Some of them are decades in production and are just coming back into the fore. Some of them are newer technologies that are being introduced. If you look at persistent memory, the two that are most common would be the standard NVDIMM, and there's various ways that that's done, but it's usually done using NAND flash. And then also Intel Optane, which is a non-standard specification, but does conform to the persistent memory specs. If you'd actually like to understand what the various hardware is, there's an excellent annual update on persistent memory that Dave Eggleston gave at the Flash Memory Summit in 2020, and you can see the link for that in the lower left-hand side of the corner. And I'd encourage you to watch that if you like to be a hardware geek. So if we look at what actually is required to be able to create that ecosystem that's going to be able to drive this fundamental change, you can look at all the different things that need to fit together. First of all, we need those persistent memory forms that I was just discussing, and you can see that on the lower left. There's a variety of vendors that are shipping that industry standard JDAC NVDIMM and continue to deliver around that. And there's also, like I said, the Intel Optane memory as well. And there's some other standards that are probably moving into this over time that I'll discuss as well. But obviously, once I have the hardware, I need platforms that are going to be able to support it. Having a fundamental memory change does require some hardware and BIOS updates. And so Intel and AMD and many of the other hardware vendors working with the OEMs are delivering platforms around that. Then you need the industry standards that are able to deliver that. So currently, if you look at the industry standards, they're mostly focused on DIMM design. So there's some various JEDEC standards that actually go into the hardware DIMM design around NVDIMM and NVDIMM-P. And I would also pay attention, I don't have it here listed on the slide, but I think some of you are probably familiar with the work going on around the Compute Express Link, or CXL, and that's its own standards body that is actually developing a hardware interface based off of the PCI physicals to be able to extend that to a variety of I/O and memory functions. And so if you look at some of the CXL functions, I actually think long-term that's where you'll see a lot of this persistent memory being delivered. Again, the latency is just slightly faster or slightly slower than that of memory, but significantly faster than an SSD in terms of going through the driver and doing all the work there. Now, once you have those standards, you need then a programming model that goes on top of that. And that's something that SNIA is focused on. And we'll get to that in a slide or two. But SNIA wanted to develop a non-volatile memory programming standard or programming model. The latest, version 1.2, was released in June of 2017. And what we wanted to do was be able to deliver a common model that could be used by software. That model was delivered in various stages, starting in Windows Server 2016. The Linux kernel 4.2 and later also supports it. So having a variety of different solutions to be able to support that, but using a standard programming model we felt was very important. So all these things really come together to change an ecosystem. So if you think about this in terms of computational storage, think in a similar way. You'll see various devices and vendors producing these things. We talked a lot about the computational storage specification, and that also, I think, will rely very heavily on CXL. And then you'll be able to see that programming model long-term get adapted in the various closed and open source operating systems. So I'm very excited for some of the work that this model will be able to provide along computational storage as well. Let me show you a little bit about the existing persistent memory programming model. If you want to see the full standard, you can actually see that in the link on the right. But the standard actually has a variety of different models. There's an application direct, basically using the standard load store capability, but we're using that in a persistent way. But we also created a very lightweight, what we call PM-aware file system in the specification, and that uses a variety of native file APIs. There's different modes that can be used, and those can be delivered down to basically an interface driver that talks to the device. So if I want to use an NVDIMM, I would have an NVDIMM PM capable driver in that space writing to those devices. If I want to use Intel Optane, same thing, PM capable driver that writes down to those Optane devices. But above that, the application just basically is using the file system and is able to work through that driver seamlessly. We've actually run some programming challenges where we've taken code that's developed on Optane and run it on NVDIMMs and vice versa to be able to prove the viability of this model. And it seems to be working fairly well. Now, the keys to any industry standard programming model are obviously going to need a consistent architecture model. We want to make sure not only that it's supported in all the open source code bases and checked in upstream, but that verbiage is also something that can be used in some of the closed source products as we deliver that. And you can see that we've delivered that in the Windows core as well. And then a variety of open source tools and libraries to be able to support that. The key one that I think you're going to want to focus on is PMDK. So the Persistent Memory Development Kit was actually developed on, using the NVM specification, and that open source code continues to get developed. You can look at pmem.io. This is a free community. You can see the specification, you can see how the code is being developed, and you can see all the extensions that are being added in. So there's constant work not only on extending the persistent memory development capability using PMDK, but also ensuring that the performance continues to improve as well. There's obviously going to be some other open source direct programming models. I think you're going to see a variety of file systems that will work on this as well. And a lot of these will be supported on their own or supported in open source in a variety of ways. From the SNIA perspective, our promise is to continue to not only be able to drive the capability around programming, but also some of the conversational opportunities that we can have. So you do have access to a persistent memory hackathon, and I'll show you how to get to that today, and I'll actually do a quick demo of some of the things we're doing there. And this is something that we do worldwide, and we actually have some systems that are available in the cloud 24/7, 365 and a quarter for you to be able to use currently. We do, on occasion, offer programming challenges. We had a great NVDIMM programming challenge that we did a couple of years ago where we actually invited people to take advantage very specifically of some of the NVDIMM characteristics. And we plan to offer other programming challenges moving forward. But we've also focused on a new industry-focused conference that's Perl, Persistent Programming in Real Life, and I believe it's pearl.nvsl.io. You can go there. This is something that SNIA does in conjunction with UCSD and San Diego, and we focus really on having a conversation here. This is industry professionals who are writing and developing code today, talking to each other about what it's like. For instance, a lot of the things that we do in here, we actually have people show the code that they're developing to be able to demonstrate what's easy and what's hard about doing some of these programming models. So it's a great way to be able to drive that opportunity. So again, all these things, you know, a standard open source development kit, some programming models, and then the various conversational opportunities that can come around those are things that you should be able to expect from SNIA long term in terms of computational storage. Now, what do we do at a hackathon? Well, you know, obviously we're trying to focus on the programming model, and we talked about the different programming challenges. But if you want to look at a hackathon, you can do it right here. That's PMM Workshop at sniapm.io, and PM Workshop at sniapm.io. Error on the slide there. And you can request access. You can request access to that with the passcode PMDK. You can also get to that from the SNIA link, and I'll show you how to do that. And then we'll be offering various hackathons as we go up, but that is pmworkshop.sniapm.io. And then you can use. You can also, if you want, host your own hackathon. I've actually given you the link on the bottom there for the Git repository for the PMM hackathon. So you can actually test your PM software on your own system. You can create your own system. It actually doesn't require you to have PMM in the system, but it certainly helps if you do. So if you have a PM enabled server, or you can get access to one in the cloud because they are offered, then you can actually go create the software and load it. And there's some good readmes that are up in the Git that would tell you how to do that. Let me show you a little bit about what we do at a hackathon. So we created a fairly simple interface. So this is a pretty simple interface in terms of providing a set of different examples. So I can just click on an example. So when you log in and request that access with the PMDK code, you'll get your own username and login, and you'll be able to go in and see these examples. These work from just standard mapping of persistent memories to some basic transactions, key value stores, low-level persistent hacking using some of the various PMM check tools, and all the way up to some low-level programming examples in Java, which were recently added. And I think those are really fun. But let me show you just a variety of different things that we can do here. So first of all, if you look, we describe a little bit about what the programming example is doing, going through an mmap and an msync. We talk a little bit about what the runtime environment looks like, and this is configured in what's called an FSDAX mode. If you want a description of all the different modes or others, there's actually some background slides that give you an idea of the programming model and some of the different modes that can be used. And you have the ability there, if you want to hop into a shell window, you can do that. But what we're doing here is we're making it pretty bandwidth friendly. We actually created a shell, and so we have code that's available here in the shell. And what I can do is I can just use that program right there, and I can go build that program. That's actually sending the code that's on your system up to the server environment where it's compiled, and then the results are returned. And now you can see I successfully configured and built one there. Here I can, but I can show you. Oops, I can show you that the shell is, is pretty easy to interface with. I am not a developer myself, at least not for a very long time, so I'm not going to mess with the program too much. But you can see I just changed the string, very simple, and managed not to crash the program in the process. Now, then we have the run shell that would come down there, and I can now click to run that. Again, that code gets sent back to the server and gets sent down, and you can see as I do a dump from my mmap file that you can see that my program is my string is persisted there. So like I said, there's a variety of different programming examples that come in, and we'll continue to add to these. I certainly want to thank Intel has been doing a significant amount of work on many of these examples, as well as creating the shell. And I certainly want to thank the team there for working with SNIA to be able to produce this. So again, if you want to see, all of that's available at the GitHub, so you can pull down that code and start playing on your own, host your own hackathon. We at SNIA are more than willing to help, and you can see the email there, pmhackathon@snia.org, and we'd love to be able to help you understand how to be able to deliver that. If you want to see some additional resources, you can go to SNIA.org PM, or SNIA.org PM Hackathon is the workshop page. So if you click on that link, you can actually see there's a video of Andy Rudolph, who's actually giving you an idea of the programming model, and we're going through the slides that you actually see up on the hackathon page itself, and then a link to the hackathon so that you can move in. You can also see what's the latest going on in the computational storage, and I'm sure you've seen that in the last few presentations as well. You can follow on Twitter, SNIA CMSI and SNIA Computation, as well as the Compute Memory and Storage blog. So I just really wanted to spend that time to give you a taste of the various things that could go on. So look at what we're doing on persistent memory and the work that we've done and how we've enabled the hackathon, and project forward to what we'll be able to do with computational storage and many of the other initiatives that you'll see coming out of CMSI over time. In addition, you should probably look on CMSI page to see some of the work that we've been doing around performance tests and some of the other work that we've been doing with the technology working groups. So I want you to certainly, look at those resources and take a good look at some of the things that SNIA can do for you in your open source development. I certainly want to thank you today for your attention. I want to thank you for attending this track. I know that I'm closing it out, and so I hope that you have a great day and that you have a great rest of your SODACON conference. Thank you very much.